Hello, students. So, in this class, we will be discussing chapter number 1, which is the real number of class 10 NCERT. So, in class 9, yeah, you begin your exploration of the world of real numbers and encountered irrational numbers. So we continue our discussion on real number in this chapter also. So we begin with two very important properties of positive numbers in this section 1.2 and 1.3. So we will be making a two videos on section 1.2 and 1.3, namely the lucid division algorithm and fundamental theorem of arithmetic. So lucid division algorithm, as the name suggests, yeah, has to do with divisibility of integers. I am sure everyone is okay with the word integer here. Positive numbers, negative numbers, zero are all integers. Stated simply, it is like any positive number can be divided by another positive integer in such a way. Yeah, a positive number, let's take a positive number a divided by any other positive numbers in such a way that it leaves a remainder r that is smaller than b. Yeah, the number which is divided by. So many of you probably recognize this as the usual long division process. Although the result is quite easy to state and understand, it has many applications related to the divisibility property of integer. So we touch upon a few of them and use it mainly to compute the HCF. Okay, the HCF of two positive integers. Now, the fundamental theorem of arithmetic, on the other hand, has to do something with the multiplication of positive integers. Yeah, you already know that every composite number can be expressed as a product of prime in a unique way. Okay, when you multiply uh, two prime numbers, yeah, you will get a composite number for any composite number you can take. This important fact is called the fundamental theorem of arithmetic. Okay, again, while it is a result that is easy to state and understand, it has a very deep and significant application in the field of mathematics. So we use the fundamental theorem of arithmetic in two main applications. First, we use it to prove that irrationality of many of the numbers that we studied in class 9, such as root 3, root 2, root 5, which does not have a perfect root. Second, we apply this theorem to explore when exactly the decimal expansion of a rational number, let's say P upon Q. Take two number P and Q, wherein Q is not equal to 0, is terminating, and is no, when it is non-terminating, repeating. So we do so by looking at the prime factorization of the denominator Q of P upon Q. So you will see that the prime factorization of Q will completely reveal the nature of the decimal expression of this P upon Q. So let us begin our exploration on the fundamental theorem of arithmetic. So in your earlier classes, you have seen that any natural number can be written as a product of its prime factor. Let's take an example. Let's take 2. So we write it as 2. If I say 4, we write it as 2 times 2. And if I say like 2, 5, 3. Okay, so which two number we are going to multiply? 11 times 23 and so on and so on. Now let us try and look at natural numbers from the other direction. That is, can any natural number be obtained by multiplying prime number? Let's see. Take any collection of prime number. Let's take 2, 3, 7, 11, and 23. So all these numbers are prime numbers. So if we multiply some or all of these numbers, allowing them to repeat as many times as we wish, we can product a large collection of positive integers. In fact, infinitely many. Let us list a few of them. Okay, 7 times 11 times 23. Okay, These are three prime number. If you multiply, you will be getting 1771. Similarly, I can even repeat the prime number like 2 times 3 times 7 times 11 times 23, which is equal to 10626. So this is all from the NCERT textbook syllabus, which we are discussing here. All the questions we will be taking from the NCERT syllabus itself. Okay, suppose I am multiplying 2 3 times. So I can simply write 2 to the power of 3, or what we called it as 2 cube, multiplied by 3 into 7 to the power of 3. 7 to the power of 3 means 7 cube, wherein we are multiplying 7 3 times. 8, 2, 3, 2, and so on and so forth. Now let us suppose your collections of prime include all the possible primes. What is your guesses about the size of this collection? Does it contain only a finite numbers of integer or infinitely many? In fact, there are infinitely many primes. So if we combine all of these primes in any possible way, we will get the infinite collections of numbers. So all the primes and all possible products of prime, the question is, can we produce all the composite number in this way? Like all the numbers, a bigger number, a 4-digit number, a 6-digit number. Do you think that there may be a composite number which is not a product of the power of the primes? Before we answer these, let us factorize positive integer, that is do the opposite of what we have done so far. Okay, let us take a number. The number is 32760. Okay, we are going to target this number with the prime number. So first we will be starting with the number, the smallest prime number 2. So 2 ones are 2, 2 6s are 12, then 2 3s are 6, again carry 1, 2 8s are 16, 0. So this is the first time we have targeted the number with the first prime number 2. What do you think? Again, we can target this number with the smallest prime number, that is 2. Let's see. 2. 2 times 8 is 16, 2 ones are 2, 2 nines are 18, and a 0. Very good. Till here, everything is going well. Again, I think we can target with the number 2 as 0 is there in the units place. So 2, 2 4s are 8. So we are going to take two numbers from here. So definitely we are going to put a 0 as we do in division as well. 2 nines are 18, carry 1, 2 5s are 10. Again, I think that's a time come to target the number, but not this time too. Yeah, because in the ones place we can find it the number to be 5, which is an odd number. So let's target with some other 5. I think 3 would be better because 3 5s is 15. So 3 ones are 3, 3 3s are 9 because carry 1. Again, 1 is carried, 3 6 are 18, 1 is carried, 3 5s are 50. Moving further, let's target this number 1365. Okay. So we will target it with 3, 4, 5, 5. Again, simply we will move further by targeting the number. The next number we are going to target is 455 by the next prime number, which is 5591. And the next number 91 we are going to target. What do you think, students? Which prime number we should take? Yes, it can be 7 and 13. So we are going to use this factor tree, yeah, which are giving you an answer which is similar to the previous one. Yeah, but we are going to do it in a reverse mode because such a big composite number, we have to use the prime factorization. So we have factorized 32760 as 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. Yeah, as the product of the prime number. So we can say that 32760 is equal to 2 to the power of 3 because 3 times we are multiplying 2 and 3 to the power of 2 multiplied by 5 multiplied by 7 and the last number product of 30. So as the product of the power of prime. Let us take another number. Yeah, and I want you all to be giving a try and tell me in the next class how much you got. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can even comment in the chat, even comment down the answer. Which prime numbers are you going to take to get the prime factor of this number? So this led us to the very composite number can be written as the, like every composite number can be written as the product of the power of primes. So in fact, this statement is true that it is called as fundamental theorem of arithmetic because it has basic crucial importance to the study of integers. Now let us formally state this theorem. Yeah, theorem number 1, which is fundamental theorem of arithmetic. Every composite number can be expressed or factorized as the product of the prime, and this factorization is unique apart from the order in which the prime number occurs. The 2 can come later, 3 can come first. That is absolutely okay. Yeah, that does not make any. And equivalent theorem of version of theorem 1.2 was probably first recorded in this book of Lucid Element. Yeah, Lucid has a whole set of books, Element, and each and every part is considered as a book before it came to known as the fundamental theorem of arithmetic. Yeah, so he has fundamental contribution to both mathematics and science. Yeah, this is for just for a knowledge check. We will be exploring more about fundamental theorem of arithmetic in the coming class, and we are also going to solve exercise number 1.1, which is there in your textbook NCERT.